Recording's running. Yep. Okay. Okay. This question. Okay, so this is a free body diagram, something you should be comfortable drawing at this moment. And we need to, so in this case, it's probably the first time where like you've given a free body diagram and asked to sketch back to the actual like illustration. And this is, I think it was at the very end of the Newton's second law tutorials, tutorial 3. So the stuff I didn't get to at the very end. This question was there. So we have a situation, we've got a weight, we've got a normal force. I guess you could look at a couple of different things. Where is this on a horizontal surface? If you try to look at the number of boxes here, there are 1, 2, 3, 4, 5, 6 boxes going down. There's 3 boxes going up from the normal, but there is a component of the tension here, three boxes. So this would seem that the net horizontal, net vertical force is 0. So I'm going to assume it's on the and the normal force, of course, is straight up. So that's even a stronger indicator that it's on a horizontal surface. And the tension is pulling here, since this is 3 and 3 boxes. That's a 45-degree angle. So I can think of this is a tension force here at a 45-degree angle. Any questions on that? Okay. For this question, I'm going to do a raise of hands. So at this instance, could the cart be moving to the left? Okay. Moving to the right. Okay. Stationary. Okay. I want you to rethink about the question. Oh, no, yeah. Another one of those questions. Chat with your neighbors. Why I'm asked, think about the fact that I'm like, could it be moving to the left? Could it be stationary? Could it be moving to the right? No, I just added it in just for extra. It's no harm, like, the question would ask, I would say like sketching, like a quantitatively correct or like a semi-quantitatively correct. So maybe to add the angle in. You can determine it again from the, but not really. No. Okay, I'll do a raise the hands again. Could the car be moving to the left? You're saying yeah? Right. Somebody over here is going. Could it be moving to the left? Somebody like tentatively saying that. Moving to the right, you're still confident there. Could it be stationary? More hands for stationary than moving to the left. Okay, so this is a, I don't want to say it's not a trick question. I like the question a lot. So this is trying to hammer home a really important concept. And this one question does it pretty well. So what is the direction of the net force on the cart? So we definitely know that the net force is to the right. And that's sort of like 3 boxes on the diagram. But so then I know the direction of the acceleration is to the right. So think about your kinematics and how much I spent time on talking about the difference between V and A. Does a rightward acceleration mean the object's moving to the right? No. Does it mean it's stationary? All right, could it be stationary? Yes. Could it be instantaneously at rest and just about to move to the right? Yes. Could it be moving to the left and slowing down? Yes. Could it be moving to the right and speeding up? Yes. So it could be, the acceleration tells you nothing about the movement, only the change in the movement. That's something really important. Again, not to confuse A with V. Don't worry. Again, it's not. I give this to graduate students. They all say the same thing. It's moving to the right. It's obvious. I'm like, no, not really. It's the acceleration to the right. Yes, but this car could be going to the left, and you're trying to slow it down, so you're tugging it to the right. Maybe it's instantaneous at rest. It's at 0, and you're trying to get the car moving to the right. Or maybe it's moving to the right, and you're pulling in, and it's accelerating to the right. The only thing you know for sure is accelerating to the right. You actually don't know anything about its movement unless you knew something about its initial velocity. So it's sort of a question, kind of a conceptual question to reinforce the idea that the A only tells you about how the velocity changes, not about the actual initial velocity. And in addition to that, the net force can only tell you something about the acceleration and not about the velocity. In order to figure out like if it's slowing down or speeding up, you need to know like what is its V and what is its A. Are they the same sign or the opposite sign? You can go back to all that stuff in kinematics.
Wait, can you explain why it can be stationary?
So it could be instantaneously at rest. It's like it's at rest, and I just at this instant in time, I pull on it. So it's at rest, and it's just about to move to the right.
Oh,
Yep.
So net force has nothing to do with motion, or like direction of if it's going this way or that way. It's just the direction of the force, but not of the object.
So that's a great question. So I'll repeat it for the mic. So the question is that I'm trying to repeat what you said, that the F net tells us nothing about the direction of the motion, and it only gives you the direction of A. That's most definitely correct. The net force only tells you in what direction will the object accelerate, not the direction it will move. And that's almost the biggest thing you have to overcome in 114, is that misconception, is that students tend to put the net force in the direction of motion. It's only in the direction of the acceleration. And that's how a lot of the stuff we have to overcome. So again, if it was moving to the left and I wanted to cause it to slow down, you would pull it on it to the right. That's natural, right? Because you want the acceleration to oppose the velocity in order to slow down. So yeah, FNet only tells you about the direction of A, the acceleration, and that only gives you the direction of delta V, not V.